This section examines sources of emission from light vehicles. The term emission normally refers to the pollution produced by a light vehicle during normal use. Emission control systems are designed to limit the pollution caused by the harmful products of storing and burning fuel. Emissions from a petrol-driven motor vehicle usually come from four sources: the fuel tank, the carburetor, the crankcase, and the exhaust system. The fuel tank and carburetor allow fuel to evaporate and escape to the atmosphere. These are called evaporative emissions. The crankcase and exhaust system emit pollutants directly from the engine into the atmosphere. They are caused when hydrocarbons, lead compounds, and oxygen and nitrogen from the air are burned in the combustion chamber. In a compression ignition engine, emissions originate from the engine and escape to the atmosphere from the exhaust and the crankcase breather. This section examines hydrocarbons. Petrol, diesel, LP and natural gas are all hydrocarbon compounds. Hydrocarbon emissions react with other compounds in the atmosphere to produce photochemical smog. Hydrocarbons are a major source of motor vehicle emissions. Petrol needs to evaporate easily to burn properly in an internal combustion engine. But this property also means it evaporates easily into the atmosphere at ordinary temperatures and pressures. When a vehicle is being refueled, hydrocarbon vapors can escape from the filler neck into the atmosphere. When the vehicle is left in the sun, its temperature increases and fuel evaporates from the tank and, if there is a carburetor, from it as well. An evaporation control system is fitted to modern vehicles to collect and store the hydrocarbon vapors from the tank and the carburetor. Then, when conditions are suitable, these vapors are then drawn into the intake manifold and burned as part of the combustion process. In a petrol engine vehicle, during an engine cycle, some of the gases escape past the piston rings into the crankcase. This is called blow-by. Some of these blow-by gases mix with heated vaporized oil and can usually escape out into the atmosphere. Modern vehicles direct these gases and vapors back through the inlet system to be burned during normal combustion. Hydrocarbons can also be part of the exhaust gases. In a four-stroke petrol engine, during valve overlap at top dead center, some intake charge is drawn out of the combustion chamber into the exhaust port. Raw fuel, a mixture of hydrocarbons and air, is released into the atmosphere. When combustion occurs in the cylinder, the walls, piston and piston rings are slightly cooler than points closer to the burning mixture. Some of the air and fuel molecules come in contact with these cooler parts and they cool down until their temperature becomes too low for combustion to occur. They are left unburned, and when the exhaust port opens, they leave the cylinder. Misfiring of the ignition can result in unburned fuel leaving the cylinder when the exhaust port opens. If an excessively rich air-fuel mixture is used, there is too much fuel for the quantity of air. Combustion will be incomplete, and any unburned fuel will leave the cylinder through the exhaust port. If an excessively lean mixture is used, then combustion takes longer, and the flame may extinguish before it is complete. When the exhaust port opens, unburned hydrocarbons will be exhausted from the cylinder. This section examines oxides of nitrogen. Air that's drawn from the atmosphere into an engine contains almost 80% nitrogen. Under the high temperatures and pressure of combustion, this nitrogen combines with oxygen to produce oxides of nitrogen. Almost all internal combustion engine exhaust gases contain these chemicals. They are more likely to be produced when high peak temperatures occur during combustion. If a lean mixture is used, formation of hydrocarbons and carbon monoxide is reduced, but for oxides of nitrogen it is increased. This is due to the high temperature and the increase in available oxygen. Oxides of nitrogen are claimed to be major contributors to photochemical smog. Compression ignition engines can produce high levels of oxides of nitrogen. Oxides of nitrogen irritate the eyes, nose and throat. In extreme cases, coughing and lung damage can occur. This section examines particulates. Particulates from modern engines are usually carbon-based. Older vehicles may produce lead-based particulates. This is caused by lead compounds used in the fuel to raise its octane rating. In spark ignition engines, particulates are caused by incomplete combustion of rich air fuel mixtures. In compression ignition engines, they are caused by a lack of turbulence and lack of oxygen. This section examines carbon monoxide. Carbon monoxide is an extremely poisonous gas. Inhaling it in a confined space can be lethal, and since it has no odor or color, it is very dangerous. It is produced during combustion when there are not enough oxygen molecules around the hydrocarbon molecules. This can be caused by an incorrect air-fuel ratio. In modern vehicles, carbon monoxide emissions have been reduced by better engine designs and by chemically treating the exhaust gas. This section examines carbon dioxide. Carbon dioxide is produced with water when complete combustion of air and fuel occurs. It isn't poisonous, but many scientists consider it a serious contributor to global warming. Catalytic converters in petrol engine vehicles convert carbon monoxide to carbon dioxide. Carbon dioxide is also produced by diesel and LPG fueled vehicles. This section examines evaporation emission control systems. Early vehicles vented the fuel tank through the filler cap into the atmosphere. Some of the fuel in the tank would vaporize. Some vapors escaped from the filler cap, some from the carburetor. Non-vented filler caps are designed to stop the exit of vapors. A vacuum relief valve can relieve low pressure in the tank when the temperature drops. This will also stop the tank from collapsing if its internal pressure falls below atmospheric pressure. The fuel cap may also incorporate a pressure relief valve. If the tank's internal pressure exceeds the set value of the relief valve, it can stop the tank from rupturing. Some modern caps have no valves at all and are completely sealed to stop the entry of air and water, as well as the emission of fuel vapor. Modern tanks also contain an expansion volume either directly in the shape of the tank or in a separate chamber connected to the fuel tank by tubing. A liquid vapor separator may be connected to the tank by a number of tubes. This separator allows liquid fuel to separate from the vapors and return to the tank. A vapor line is connected to the vapor space in the tank, or the liquid vapor separator. It carries fuel vapors from the tank to a storage volume. This vapor line can incorporate check valves. If the vehicle is tilted too far from the horizontal, they stop liquid fuel entering the storage volume. A storage device is used to store the fuel vapors. The fuel tank breathes through this storage device. Some vehicles use the engine crankcase. When the temperature of the fuel in the tank increases, fuel vapors are forced along the vent line past a liquid check valve and into the crankcase. When the engine starts, the positive crankcase ventilation system flushes vapors out of the crankcase and into the intake manifold, where it joins with the inlet air-fuel mixture. Once in the inlet manifold, the vapours are drawn into the engine where combustion can convert them into carbon dioxide and water vapour. Another kind of storage device is a canister of activated charcoal. Activated means the charcoal is porous with a large surface area. It can store large quantities of fuel vapour. It has connections for the fuel tank vent line and the purge line, which carries the vapours to the intake manifold. In some designs on carburetted engines, it also has a connection from the carburetor bowl. When the engine is running, the action of the piston during the intake strokes creates a low pressure area in the inlet manifold. This can be used to open a purge valve, which draws fresh air into the bottom of the canister. The air collects the vapour and directs it to the inlet manifold, where it is drawn into the engine and burned. The purge valve is designed to operate only at speeds well above idle. If it operated at low speeds, the extra fuel vapours could upset the air-fuel mixture, which could cause poor idling and rough running. The evaporation of automotive fuel is a major source of hydrocarbon emissions. The rates of evaporation are higher with petrol than diesel because petrol is more volatile. This section examines crankcase emission control. While the engine is running, some gases from combustion leak between the piston rings and the cylinder walls down into the crankcase. This leakage is called blow-by. Unburned fuel and water from condensation also find their way into the crankcase and sump. When the engine reaches its full operating temperature, the water and fuel evaporate. To prevent pressure build-up, the crankcase must be ventilated. In older vehicles, crankcase vapours were vented directly to the atmosphere through a breather tube or road draft tube. It was shaped to help draw the vapours from the crankcase as the vehicle was being driven. Modern vehicles are required to direct crankcase breather gases and vapours back into the inlet system to be burned. A common method of doing this is called positive crankcase ventilation, or PCV. A valve called the PCV valve regulates gas flow between the crankcase and the inlet manifold. It is controlled by the pressure in the manifold. With the engine off, the valve is closed and air cannot enter the inlet manifold. This allows the engine to start. At idle, low pressure in the manifold draws the valve to the other end of the body. This lets a small, measured amount of vapour pass the valve. At wider throttle openings, the valve plunger position allows maximum flow through the body, which gives maximum crankcase ventilation. The system is designed to remove more air than just blow-by, so there's a fresh air intake, usually at the air cleaner, to direct filtered air to the crankcase. This intake is usually as far as possible from the PCV valve. Wide throttle openings produce maximum blow-by. Gases that can't be handled through the vacuum system are directed back through the inlet connection to the air cleaner, where they join the carburetor intake air and are drawn into the cylinders for burning. This section examines combustion control. Approximately 60% of emissions from an uncontrolled vehicle engine come from the exhaust, a result of combustion of the fuel and the air. To reduce these emissions, some devices or systems control the combustion process itself, while others treat the resulting exhaust gases. Most modern vehicles use a combination. Carburetors meet emission standards by maintaining accurate mixture control over a full range of engine conditions. To achieve this, most carburetors require an air supply at constant temperature. A heated air inlet system uses hot air collected from near the exhaust manifold and mixes it with outside air. One control system uses a temperature-sensitive valve inside the air cleaner. It operates a flap that blends the hot air with cool air, so that the carburetor receives air at about 40 degrees Celsius, regardless of outside air temperature. Maintenance of this temperature assists vaporization of the fuel, particularly when the engine is cold. Vaporization is also assisted by heating the intake manifold, normally by circulating hot liquid coolant through passages in the manifold. If a manifold is too cold, fuel condenses on its inner surfaces, which will create a lean mixture and may cause incomplete combustion. Carbon monoxide and hydrocarbon emissions are highest from a cold engine. Changes in operating conditions can change mixture conditions within the manifold. If a carbureted engine is being driven at moderate speed and the throttle is suddenly closed, any fuel condensed on the manifold walls is drawn into the cylinders. The low pressure in the manifold also acts on the idle circuit in the carburetor to cause a larger amount of fuel to flow from the idle discharge port. All of these factors enrich the mixture entering the engine. There is only a relatively small quantity of mixture in the combustion chamber at this point, so turbulence tends to be poor. This can lead to incomplete combustion and the release of unburned gases into the exhaust. The throttle positioner and dashpot slow down the rate of closure of the throttle plate. This allows more time for air to enter the manifold and for the fuel to vaporize before the throttle is completely closed. A more combustible mixture is thus formed, which leads to complete combustion and a reduction in hydrocarbon and carbon monoxide emissions. Combustion chamber design can affect the combustion process also, and therefore the level of emissions. Designs that increase gas flow rate and promote vaporization distribute the fuel more evenly in the combustion chamber. Quenching of the combustion flame can occur in zones in the combustion chamber where surface temperatures are low. The flame temperature drops so low in these areas that the flame goes out or is quenched. Fuel left unburned in these zones is then exhausted as hydrocarbon and carbon monoxide emissions. If the spark plug is positioned so that the flame front travels evenly through the combustion chamber, combustion is more complete. Gas flow rate and volumetric efficiency can be improved by using 2 intake valves in each cylinder. The effective port opening is increased and the gas flow rate increases. Changing valve timing also alters the combustion process. Reducing valve overlap reduces the scavenging effect. It also reduces hydrocarbon emission. If valve overlap is maintained or even increased, oxides of nitrogen can be reduced by an exhaust gas recirculation or EGR valve connected between the exhaust port or manifold and the intake system. If engine conditions are likely to produce oxides of nitrogen, the EGR valve opens, letting some gases pass from the exhaust into the intake system. During combustion, these exhaust gases absorb heat from the burning air and fuel. This lowers peak combustion temperatures, which reduces the formation of the oxides of nitrogen. The EGR valve usually opens when the engine is at normal operating temperature and likely to be using a lean mixture. When the engine first starts and until it warms up, a temperature-sensitive valve prevents manifold pressure reaching the EGR valve and stops it from operating. Manifold pressure reaches the valve when the engine is warm, and when the EGR port of the carburetor is influenced by the position of the throttle. This is generally at light throttle openings, when a lean mixture could cause increased oxides of nitrogen. It does not operate at idle or at wide open throttle. Oxides of nitrogen can also be reduced by retarding ignition timing. This lowers the maximum temperature reached during combustion. The maximum ignition advance setting is then said to be emission limited. However, it also lowers engine output and increases fuel consumption. Spark control systems use ignition timing to optimize engine output and fuel consumption with minimal emissions. They control vacuum levels to the vacuum advance unit on the distributor. In some designs, vacuum signals are delayed with vacuum valves in the signal line. In other designs, the vacuum signals are sustained. The signals can also be applied to dual diaphragm advance units on some distributors. The degree of control needed depends on many other factors, and each application should be considered individually. If the exhaust gas is hot enough, combustion of remaining hydrocarbons and carbon monoxide can be completed by adding extra air to them at the exhaust port or manifold. This afterburning produces water and carbon dioxide, which are then exhausted to the atmosphere. The pulse air method uses the pulsations of the exhaust gas to open and close a reed valve. It admits air into the exhaust manifold in short bursts. Air drawn from the air filter enters the exhaust manifold. This method suits engines with 4 cylinders or less, because their exhaust pulsations are further apart. Larger capacity engines may use an air pump to supply a larger volume of air. The pump is normally driven by a V-belt from the engine crankshaft and forces air into the exhaust ports. Some of the engine's output is used in driving the pump. Electronic fuel injection and engine management systems deal with emissions more effectively than carbureted engines by more closely controlling the air-fuel ratio entering each cylinder and by ensuring the ignition timing matches operating conditions. Sensors around the engine send the ECU information about airflow, coolant temperature, throttle position and engine speed. The ECU uses this to set fuel and ignition settings from its programmed memory. Most systems also use a sensor in the exhaust manifold to gauge the amount of oxygen in the exhaust gases leaving the engine. This indicates how well combustion is being completed, which in turn indicates the air-fuel mixture entering the engine. A voltage signal is then relayed back to the control unit to indicate whether the mixture is rich or lean. More oxygen indicates a lean mixture. Less indicates a rich mixture. The control unit then adjusts the amount of fuel being injected into the engine to keep the air-fuel ratio very close to the chemically correct composition for complete combustion. By mass, this is 14.7 parts of air to 1 of fuel, known as the stoichiometric ratio. Maintaining the stoichiometric ratio within close limits is necessary for the catalytic converter to operate efficiently. It fits into the exhaust system like a muffler near the exhaust manifold. It receives all of the exhaust gases from the engine and chemically treats the remaining pollutants in the gases, converting them to less harmful substances. This is done by a catalyst in the converter. A catalyst causes a chemical reaction, but after the reaction ends, remains unchanged itself. The catalytic converter has a ceramic core housed in a stainless steel shell. The core contains many small passages through which the exhaust gases pass. A thin coating of aluminium oxide called alumina wash coat covers these inside passages. It has a rough surface, and it's there to provide a large surface area in the passages. The catalyst is finely dispersed over the surface of the alumina wash coat. The large surface area ensures that virtually all of the exhaust gases come into contact with the catalyst as they pass through the passages in the core. Leaded fuel cannot be used in vehicles with a catalytic converter. The lead contaminates the catalyst and stops the reactions from occurring. The use of unleaded fuel has a further benefit of reducing the amount of lead emitted into the atmosphere. Diesel engines are usually low in carbon monoxide and hydrocarbon emissions, though some do emit high levels of the oxides of nitrogen. The main problem with diesel engines is the emission of particulates, minute particles of carbon, visible as black smoke. Most diesel engines of heavier vehicles use electronically controlled injectors. This has reduced considerably the emission of particulates and oxides of nitrogen.